Preparation of aspirin. Aspirin, of course, is acetylsalicylic acid. And we're going to make this today from salicylic acid. So this is salicylic acid. It has a melting point of 159 degrees. And we're going to react this with acetic anhydride using an acid catalyst. And we're going to acetylate this phenolic hydroxyl to give us our aspirin or acetylsalicylic acid. And it has a melting point of 135 degrees. And this is an example of course, nucleophilic acyl substitution. And again, the overall reaction, you have an acid or an acid derivative, and you have a nucleophile, and the nucleophile substitutes for the leaving group. Again, you have a tetrahedral intermediate, electron pair flips up, flips back down, kick off the leaving group, and the overall reaction, of course, is you substitute the nucleophile for the leaving group. And of course, the leaving group here must be a weak base. So, carboxylic acids and acid derivatives, these react by substitution. And we know that aldehydes and ketones react by nucleophilic addition. So if this represents an aldehyde or a ketone, our nucleophile does not substitute, but it adds because you have a poor leaving group with a hydride or an alkyl carbanion. So this can only do addition. Again, these would have a poor leaving group. So what we do is we protonate at this step. And the overall reaction is that we're adding the nucleophile plus a proton across the pi bond of the carbonyl. So again, aldehydes and ketones react by addition. So acids and acid derivatives react by nucleophilic acyl substitution. Aldehydes and ketones react by nucleophilic addition, again across the pi bond. Of this carbonyl. Okay, in terms of nucleophilic acyl substitution, the acid chlorides are more reactive than the anhydrides, are more reactive than the esters, are more reactive than the amides. So reactivity goes this direction. So if we choose to make an ester, which is what we're trying to make today, we're trying to make an ester between this alcohol to make this ester, we would have to have an acid chloride or an acid anhydride. And that's what we're going to do today is we're going to use the acid anhydride. So the overall reaction is to take an alcohol and the anhydride and make the ester. So again, the overall reaction here generically is to take an alcohol plus our anhydride. And again, what we're going to do here is, again, substitution. And our leaving group is going to be this carboxylate as a byproduct. So again, if I put this as my prime, okay. Plus again, we're going to have the carboxylate as the byproduct that we don't really care about, okay. All right, so overall reaction, nucleophilic acyl substitution, the alcohol attacks, electron pair flips up, flips back down, kicks off the, again, the carboxylate as the leaving group, and you've substituted the nucleophile. Now, I would like to show you the full mechanism. Now, anytime that you have a nucleophilic acyl substitution and you have an acid catalyst, the first step is to protonate the carbonyl to make this carbon more electrophilic so that your nucleophile can attack. And so on the overall mechanism here, the first step is to use that catalytic proton. And we're going to pick up that catalytic proton. And again, the whole idea is to make this carbonyl, the carbon of the carbonyl, more electrophilic. I can draw a second resonance form for this where that positive charge is delocalized to the carbon. Okay, now here's where my salicylic acid comes in. And we're not going to do anything with that benzene ring, so I'm just going to use an aromatic circle there. And this is, again, our nucleophile. The alcohol is going to attack the carbonyl. Electron pair goes out. Now you have to keep up with the protons here. All right, so I still have a proton on this oxygen, and I have attacked this carbonyl carbon. There's my methyl group. Here is the OH, and here is going to be my leaving group. Okay, so got a positive charge right here. All right, and I can lose that proton again. The order which sometimes you show these protons leaving is not necessarily that important. Okay, I'm going to go ahead and push this pair of electrons in, and the acetate leaves as the leaving group. Sorry, that looks pretty bad. Okay, so I still have that proton on here. Again, if you exact order you do this is not necessarily that important. Okay, and we have brought our leaving group here, and again we can use it to remove this proton. Okay. And notice that this is still protonated, and that's our catalytic proton that we started with up here. And we just simply lose it to the solvent. And again, this electron pair goes back into the oxygen. And so now we have our final product. So again, as I mentioned before, anytime you have an acid catalyst, you are protonating the carbonyl to make this carbon more electrophilic, susceptible to the nucleophilic attack. And again, some textbooks will show you moving this proton over to this and having it leave as the carboxylic acid. Some textbooks will show you this, and again, not necessarily the order that you remove these protons is not that critical. Do notice that this is your catalytic proton here, and here it's coming off. So the first step, and then it's regenerated.
Okay, we're ready to do our aspirin synthesis. I've weighed out approximately 1 gram of salicylic acid. It's drifting a little bit due to the currents in here. But we'll call that 1.008 grams, okay? Okay, we're ready to do the aspirin synthesis. This is the 1, 2, 3 procedure. I'm going to take 1 gram of my salicylic acid. I've weighed out approximately 1 gram. And I'm going to transfer that to my Erlenmeyer. Okay, so that's the 1. Okay, I'm going to get 2 mils of acetic anhydride. I should be in the hood. This is actually a lacrimator, which means it will make you cry. I'm going to try to pipette 2 mils. And I'm going to try to rinse that salicylic acid down. So 1 gram of salicylic acid, 2 mils of the acetic anhydride, and 3 drops of my phosphoric acid. One, 2, 3, we'll give it a little more. Okay. Swirl. Got a boiling water bath going over here. I'll put in the boiling water bath. And we're going to let this go for about 15 minutes. Okay, this has been boiling for a while, so we're going to take it off the heat and let it cool for a moment. And I'm going to add 10 mils of water. And then we're just going to let it cool. Okay, I think we're ready to collect this by vacuum filtration. Took it a little while to crystallize, but it looks pretty solid in there now. Okay, so we're going to go over here and collect this by vacuum filtration. You've seen me do this before. We're going to turn on the water, full blast. I'm going to drop a filter disc in. I'm going to moisten it with my wash bottle. And I'm going to try to get my product notice I have some still in the flask. I'm going to try to rinse that out. Now again, I've got some of my product still in my Erlenmeyer. I'm going to transfer my product back to the Erlenmeyer and we're going to do a recrystallization. Okay, I've transferred as much of my product as I can to the Erlenmeyer. I'm going to try to rinse down a little bit of this. I scraped on the side, can't get it all. Okay, it doesn't look too bad. Again, you want a minimal amount of solvent. You can always add more. And we'll let that heat up. Okay, we got a clear solution, hot saturated solution, and we're going to let this cool to room temperature. And again, the slower the better. Okay, we're ready to collect our product by vacuum filtration. Looks like it's crystallized in there. Not the best crystals, I've had better, but I'm getting a little impatient. So we're going to go ahead and collect this. Loosen my product. Try to pour it in. I'll rinse this out. I'm going to transfer this to my watch glass, and we'll put it in the oven and let it dry. Again, not the best looking crystals. Give this a few minutes. Got this set at about 110 degrees, and should be able to see that's over 100 degrees. So I'm going to turn on my melt temp, and I'm going to set the plateau. Melting point's 135, so I'm going to set this at 125. So 125, and I'm going to start this so it will heat up to the plateau and equilibrate while we're waiting for the sample to dry. Okay, we've had this in the oven for a few minutes. Again, I'm a little impatient, but I'm going to take a small sample. And, okay, again, I'm going to pack the sample. Okay, we're ready to take our melting point. I've got the plateau set at 125. My sample, let's see if we can get that. I hope you can see that. So I'm going to hit start, and it's going to ramp up, and we're going to watch it. $132, and I may see some liquid. $133. Oh, definitely see some liquid. 134. $135. Oh, it's almost all melted. Okay, I'm ready to weigh our product. Put a piece of weigh paper, tear the balance. Again, not the prettiest product. We will call that 0.778. 0.778. So from the lab, we saw that we had about a gram of our salicylic acid starting material. Okay, and the molecular weight of salicylic acid is 138. Okay, so let's calculate the number of moles. So that's grams divided by the molecular weight of 138 grams per mole. So 1.008 divided by 138 gives me 7.3 times 10 to the minus third. So 7.3 millimoles. Okay. The procedure called for 2 mils of our acetic anhydride. To get the moles, I'm going to first need the density. It's 1.082, so 1.082 grams per mil. Milliliters cancel, that leaves me with grams. I'm going to need the molecular weight. It's 102 grams per mole. Again, grams will cancel, that will give me moles. So
2 times 1.082 divided by 102 gives me 2.1 times 10 to the minus 2. 2.1 times 10 to the minus 2. So our acetic anhydride is obviously in excess. Okay, because we got 21 millimoles of it. And our salicylic acid, this is our limiting reagent. Of course, these react on a one-to-one basis. Okay, and so to calculate our theoretical yield, let's start with 1.008 grams of our salicylic acid. The molecular weight is 138 grams per mole. I have 1 mole of reactant, my salicylic acid. For each mole of my product, the aspirin, and the molecular weight of the aspirin is 180 grams per mole. Make sure you don't use the molecular weight for the acetic anhydride. This is the molecular weight for the aspirin. So again, grams cancel, moles of reactant cancel, moles of product cancel, and I'm left with grams of product. So 1.008 divided by 138 times 180. The theoretical yield should be 1.314, we'll say 1.31 grams is my theoretical yield. Okay. From the video, we saw that the actual yield was 0.778 grams, and therefore our percent yield is again actual over the theoretical times 100 to give us a percent. And so my actual yield, 0.778 grams divided by my theoretical yield, 1.31 grams times 100 should give me my percent yield. 0.778 divided by 1.31, it gives me 59.4%. And that is my percent yield, which isn't that great, but not that bad either. Okay. Again, from the video, we'll see that the melting point was 132 to 135. Again, the literature value is 135. In the lab, you always report melting points as a range from the first appearance of the liquid until the liquid, all the solid has melted and you see nothing but liquid. So again, not too bad of a yield and not too bad of a melting point, although the appearance of the product wasn't too good. I've had better crystals than that before. Okay, thank you.